Do you have a pointer? Like
I prepare everything for you. Okay.
Thanks.
This one. This one.
Oh yes.
So please have this over there. We take the submit right before we can. Now. So firstly, I'd like to say thank you to you, Professor. Yeah, and that to us a discussion about the title of issues of and firstly, I'd like to say a little bit about ITI here. As you know, last year we have time looking together. We have the main station and looking display place of ITI, and together we have many students, bachelor student, master student, and degree student and postdoctoral student. And we'd like to know more about yourself, your talk, and information about the related trend in ITI, and especially many students of the contact here would like to have some potential opportunities to be a master or degree student in Japan and for Professor Reza. And firstly, I would like to say thank you again. And I hope that it's the first discussion of our talk together. And hopefully that we can spend more and more talk in the future. And I said to this year we spend time here. I would like to invite you and some Professor in our team or some months, 2 months or 3 months or more in ITI. And by the time you can have more idea and visibility and basically first between the VNU and RMIT, and especially from these projects, we can capture very good and potential students. Because we know that in VNU and RMIT University, we have a very good display. We know that we display large display and many students from VNU and Japan University and from international school. Many students from VNU, and they ask me that when can I work with Professor Dixon, Professor from Australia and RMIT? When I told my students that okay, so please wait for very little time. We came on with setting up everything ready, and now it is the first step and first attempt for setting up research together between ITI and RMIT, and especially Professor Reza and Abel. So thank you so much, and I think that we should welcome Professor. So we have a talk about distribute information function for multi-target checking. I like to delve a little bit about this group you are asking. So here, Professor Reza is a member of the faculty of RMIT University's especially in this school of engineering in Melbourne, Australia. And he's really in electrical engineering. And since then, Professor Reza has some career in some university in Tehran, Iran, the Super University of Technology, and University of Melbourne, and Poly is Professor and so as you know that according to the title of the episode, right, this European research area have some kind of the theory of some assessment, and especially great objective assess in a multi-active public objective. So this is so in yesterday, Professor Reza has a talk in ICSA conference. So what are so thank you very much.
Good morning, everybody. It's a great pleasure to see you all, especially seeing so many talented students here. You're so eager to learn, and I will have to talk a bit fast. My slides were designed for presentation for 90 minutes, but bring it to 1 hour, finish hopefully by 10 a.m. And but still, I hope that these stuff become useful and they give you some insight about enriching your current research. My understanding is that most of your projects are around AI, and one of the major outputs of AI algorithms are decisions. Some sort of decision is made about something. This talk is about not the AI algorithms, but the next step. How to use and combine those decisions. Of course, it is in a distributed way. You have a number of agents that are connected. Each agent is running an AI algorithm, coming up with a decision. How can we combine these decisions in each agent? The decision that it makes itself and the decisions that are being made by other agents that are connected to it. I'm coming from the School of Engineering, and therefore my agents are most of the time autonomous beings, and the decisions are about situational awareness. However, it doesn't matter. That is the application. Theory you can use in your application. It's up to you to formulate it according to your application. So this is an example of what I mean by distributed autonomous agents. This is a border surveillance operation around Australia. There are a number of autonomous agents that are surveying the border area, the sea area, or in the Gulf, or maybe military boats approaching the legal. There is, for example, car. There is another car here. There is a UAV here, another UAV here, another quad roller here. And on top of them, there are other objects of interest. These numbered ones are scanning the area, coming up with detections, using their sensors. Depending on what they are, if they are a car, a drone, quadcopter, they may have different types of sensors. They may be manufactured by different companies. This quadcopter may have a hyperspectral camera. This drone may have a very high zoom camera. This drone may have a very wide camera and a radar, and the car may have a radar, LiDAR, etc. And they are connected to each other in the distributed way. The question is, how? So, see, AI runs on board them, processing all the information that they are getting, the raw sensory information, and then some decisions are made. There is an object here. The location is here. The speed is here. There is another object here. The location is here. The speed is here. And probably the class of object. This is a boat. This is a speedboat. This is a ship, and so on. Information that each of these gather. But they are not just like very upright, discrete, finite decisions. They are uncertain decisions. Why? Because sensors have errors, randomness, uncertainty. And those uncertain decisions go with the randomness model. The question is, in each of these agents, can we use all those measures with their uncertainty in a way that the result of usually the uncertainty shrinks and we get more certainty, more accuracy in the use of this. The result would be situational awareness in each of these variables. Where is what moving, in what speed, what type or class of object is it? Here is another example. In the future roads of our urban environment, there will be autonomous cars that not only are autonomous, but also are connected to each other, sharing their information. Again, they may be manufactured by different companies, equipped with different types of sensors, but each of them form situational awareness. And then they share that situational awareness with each other. How can we combine these situational awareness locally in each car? This is car number one at time k, and then it moves to here at time k plus one. And there are other cars. 2 moves here, 3 moves this way, 4 moves this way, 5 moves this way, 6 moves this way, and so on. Each of these cars are autonomous. Let's see. And each of them have their own vector, and they work out depending on the range of their sense. They work out how many cars are around, what their states are. What is the state? In this case, it is the global location and the speed with some uncertainty. And then the car number one, which is we call ego, the same algorithm could be happening in other, receives some information from neighboring venues in the distributed world. And one needs to use all those information. How can it do that? Note that we are talking about a distributed network that varies with time. For example, at time k, the network was this. Car number one was receiving information from 2, 3, and 4 only. And 4 was receiving information from 5 and 1 and 12 only, and so on. Then these cars move. And the topography of this distributed network changes as well. So we need information fusion algorithms that can work with dynamic networks. They don't need network to be fixed. So let's get mathematical. We are engineers. We are computer scientists. So far, it was all English or Vietnamese language, spoken language, right? We want to be precise, we want to be scientific, we want to devise novel solutions. And that comes from that. Speak in mathematical. How do we define situational awareness? Situational awareness is formed like this: a set of states and labels. Here is the car, its label is L1, its state, maybe position and velocity is X1. Another car, its label is L2, state X2. And up to N cars in my region of interest. Or not just car, objects of interest that are of my interest to be included in my situation. Right? So that is what I talk about when I say situational awareness. States and labels and the number of objects. But we don't have an exact information. We always need estimates. So my situational awareness is a set of states and labels. The cardinality of these sets, which is the number of objects, n, needs to be estimated in hat, and then given the impact, a single target state estimates for each object. Remember that object class may be included in the state as well, not just location and speed. This may be object class. Is it a ute? Is it a sedan? Is it a SUV? Is it a pedestrian? Maybe it's a truck. So the class may be included in this text. Now, because of randomness, because of random variations that we may have due to central uncertainties, this is a random finite set. It means that not only the number of objects is random, you see new objects may enter at any time, objects may exit, so the number can change with time randomly. But also, each of these exits have some randomness involved because of our uncertainty. With each single object, we know we have some information. For example, there is a motion model, which relates the previous time to current time with some noise. Or we could say that there is a process formed as a line. My view of the next state given the last single object. This is called motion. Let's say you're trying to track people in this room, right? My motion model, because humans walk with very high maneuverability, when somebody is moving, my state is my location and speed. The motion model is, for example, the motion model is constant speed velocity, meaning that if I'm here and I'm walking in this way, my best next state locations are around here with this almost same velocity, but it may be here with this one, or here because I'm moving this way is very small, 0. The likelihood of looking at detecting P. So your measurement is a blob in the image. And that blob somehow it is related to the real X or part of X. For example, you X location and speed, maybe just part of X plus noise. And that relationship may be nonlinear if you have camera distortions, etc. we can actually model it like this measurement line. What you get as measurement given. So that's for single target. So what happens when you're dealing only with single target? You have a state space. This is your xk minus 1. As a result of this function model, at every time, your x may go to a number of x's, possible x's in your state space. Then, at xk minus 1, you have one measure, one detection, and it is related to x according to measurement line. And then at xk, you have another detection. In reality, you only have detections and the initialization. You have no other information coming from sensor. But you have some information that are not related to the sensor, like this, your motion model. It is related to the nature of the target that you're trying to track, right? Like a person in a room or an airplane in the sky. The movements of airplanes are more concentrated, less maneuverable than people, right? So what you do, instead of X, you process and evolve, propagate the density of X. You have applied the density of X, K minus 1. You apply this form in which this is called Bayesian filtering. For one target. This problem is very easy to solve. If this is linear and this is linear, this problem becomes Kalman filter. Kalman filter is Bayesian filter with linearity and Gaussian assumption. That these are linear and the noise is Gaussian, both in the function model and in your line. But in general, you can have your densities approximated by particles and weights, and then this becomes particle filter. When you are dealing with an unknown number of targets, such as 1, so this is your space, the number of targets randomly vary with times observations or measurements randomly vary with time. But now with measurements, you not only have noise, but also you have misdetections. For example, this is your ego vehicle. There are lots of cars around, and this is your camera looking. The camera may miss some of the cars. So not every target is detected. Some targets may be missed. Also, the camera may see an advertisement, a sign with a car on it, and detect it as a car, right? So you may have false alarms. Or other things that look like a car but are not real cars. Also, so your measurements may have noise, they may have misdetections. Sorry, thank you. I think I'm loud enough, but thank you. They may have misdetections and they may have false alarms or problems. So what do? We say that instead of single target states, we get a state space of multiple targets. And our single things are sets, random finite sets. Also for our observations, our measurements are random finite sets. The story is repeated. I think that's not working. Okay. Oh. Oh. Sorry. Oh, let's stop here. So the story is then repeated with single random finite set states. Because sometimes we have the same problem at RMIT University. Prediction and update. In prediction, using the same formula. In update, using the same formula. Only instead of integrating over one vector random variable, the state of a single object, we have integrating over the random finite set density. And in here as well. And we need to know the random finite set density. What we are propagating is the random finite set density of the multi-object state random finite set. We predict that and then update it. Can we go next slide? I think you need to sit here and just go next slide. This is not working. Yeah. So with random finite set, this is how we define integration over a set. Because we don't know the cardinality of the set. It is the sum of integration for different cardinalities, starting from when the set is empty up to when the set is infinite. And this is the density of a set. It is like this. It's integral over in subspace of your single space object would be the potential X in there. Next. Okay. Did it work? Yeah. Yeah. Let me see. Maybe the battery is low. Maybe. Okay. Okay. So what we have is labeled sets. Each object has a state and a label. I will skip this square. for each probably existing object, we have two parameters, probability of existence and density. This is one way to approximate a random finite set. Just like we approximated single objects in Kalman filter with linear assumptions, this is one way to approximate. So your random finite set has different possibly existing objects. Each object has a probability of existence and a density of its state if it exists, if the condition will be right. And what you have is your total multi-object state is the union of these single object states, which are probably exist. They may not exist. So you have a set of RLs and PLs. RL is probability of existence, PL is the density of the state. And when you know all the RLs and PLs, that's entire characterization of your multi-object state, which is random. Because depends on RL. For example, some objects, you say RL is 20%. Probably that object doesn't exist. Some objects RL is 90%, probably 60%. And then PL, maybe a Gaussian here, maybe a Gaussian there. So you see, you have uncertainty here, and this is a full density. In addition to the motion model, we have probability of survival. Probability of survival. If it is close to 1, it means that the object continues to exist from k-1 to k. And if it is close to 0, it means the probability of this is high. For example, if you're doing people tracking here, when x is near the door, probability of survival is near 0 because the person may go out. But if the object is here, then the probability of survival from one frame to the next is close to 1 because there is no way that the object disappears, right? I would skip these. In addition to the motion model and probability of survival for probable exit of objects, we have a birth model. The birth is for entry of objects. For example, in here, there are two doors. So I model my birth by a labeled Multi-Bernoulli, two possibly existing objects. One is at any time, I have one object existing with a low probability. But then that probability, if there is a measurement turning it, that probability will go high in the next step, okay? So I initiate at any time an object entering from here and entering from there. The density of these objects are high around this x and very small around this x. So one object with a density that is high around here, one object that with a density that are high around that, with probability of 2%. As I said, if then I do detections, and there are detections in those areas, those probabilities of existence of 2% become large. So this is the way I model birth. So I model motion dynamics, I model exit, and I model birth, depending on my application, right? This is an application in multi-target tracking. For example, you have got a radar that is scanning this area, and objects may enter from different four edges, right? In this example, the ground truths, which I don't know, but it is the ground truths simulated, include 10 objects entering at different times. At time 1, there is one object entering at this location with this speed. At times, at times 10, there are 3 objects entering from 3 different edges, and so on. And this is how I label those. So at any time k, I label the new object. with two numbers, the time of entry and an index, just in case I have more than one objects entering at the same time, like this. So these three, their labels become 10.1, 10.2, 10.3. Because they are really entering, when I label them in the burst process, there are detections associated with them. So their probability of existence becomes high. But I create these burst particles at any time, and they die unless there are detections associated close. So what I do is, if I want to model this scenario, what I do is I have four edges, right? I take four probably entering objects, four components. One with stage location around here, one with location in this area, one in this area. And then for each of them, the speed may randomly vary from here to here, in this direction, from this angle to this. And then the speed of all objects that may enter here. So these are uniform distribution zones for each of the four possible vertices entering from each edge. I have written a book called labeled Multi-Bernoulli filter, a comprehensive design for practitioners. In that book, I have given this example and I have explained the complete MATLAB code line by line. Also, I have put the MATLAB code in GitHub. So you can use the MATLAB code to solve any multi-object tracking problem that you have. This is another example. You see, a car is moving here. I have road information. So what I have for probability of birth, if one object may enter the detection zone of this car from here with this derivative, one object may enter the detection of this car from here with this derivative. Also, there are fifth exits. So around here, the probability of survival of existing labels is small. Around here, they are small as well. This is incorporating of route information into your tracking. If you're tracking routes, that would be the airway information. If you're tracking ships, that would be other information. What matters is that in the LNB filter, labeled Multi-Bernoulli filter, you use the motion model, the entry and the exit model, all mathematically modeled, incorporated into your filter. But to be able to do computation, we approximate each single object density with weights and particles. Single object density. So with every single object, it is a vector, and you have a lot of particles for these vectors. If it is a density like this, there is a particle here, 1,000 particles. And they are given weights. So the particles that are around the peak, they have higher weights. But this is the mathematical model of the density as the sum of Dirac deltas around the particle weighted. Do you know Dirac deltas? You have seen them, right? In signal and systems or control systems, if you're coming from electronic background. So, for every single object, what I need to propagate is these particles and weights. Okay. So, in a prediction step, what happens is that I need to first calculate this guy, which is the integral of probability of survival, and then multiply it by previous probability of existence to get a predicted probability of existence.
So you have a lot of labels possibly existing with probability of existence. You multiply them by the probability of survival. So if at time k-1, there is an object here with a probability of existence of 90%, but the speed of the object is this way, right? So when you do prediction, motion models give you some particles, because there are 1,000 particles around here. Those particles are propagated according to motion model this way, because the speed is this way. So in K, you will have 1,000 particles around here. And the probability of existence is the 90% that you have multiplied by PS, probability of survival, which is now a small number because you're close to 4. So these particles will have all will be associated with one object that has a small probability of existence because it can get out its door. And then, so you propagate your particle according to motion model. And again, the weights of particles are also multiplied by PS, but they need to be renormalized because the sum of all particle weights must be 1. For measurements, we have probability of detection, we have false alarms and measurement like this, right? So we have probability of detection, which is generally a function of steps. For example, objects that are closer have a higher probability of detection, objects that are farther have a BP that is smaller. For each detection, we have a likelihood function. For example, if your detection equals a matrix H times your state, then there is plus noise, is covariance of noise, and your noise is Gaussian. Then your likelihood function becomes the Gaussian of the Z around H times H with covariance of R. For Potter, we usually model it as a Poisson random finite set. It is a random finite set that its cardinality is Poisson, and given the cardinality, its members are RMIT independently distributed from the state space. Normally, we take that independently and identically distributed uniformly. Usually, we use uniform distribution for the state of false alarms, but the number of false alarms is normally Poisson distribution, and that is the parameter of your model, which is the average or mean number of false alarms per scan. So you model your overall measurement set as the union of these guys. The measurements that are associated with target labels plus the false alarms that are Poisson random finite sets. And after prediction, you apply this guy right through, given the measurement likelihood function, to update your posterior. Your posterior becomes the updated probabilities of existence and updated single object density, right? After you have that updated R's and updated B's, the first thing that you do for estimation, you look at which R's are greater than an threshold. For example, greater than 50% or greater than 70%. Then in your estimate, you say, okay, so I have the target here, because their probabilities of existence are greater than the threshold. After that, for each target, or for each object, you use this formula, which is the weighted average of all particles with particle weights. This gives you an EAP estimate of the state. So for each object, you have the particles and weights. The weighted sum of particles gives you the EAP estimate, expected a primary estimate, right, of the shift state. This is an example of the same scenario with randomness, different random entries and exits with lots of false alarms, and you see a lot of misdetection. The probability of detection is 90%. So 10% of targets are not detected at every time, right? And this is the cardinality that the filter, the label Multi-Bernoulli filter returns every time. And these are the trajectories. Why do we have trajectories? Because we have labels. Because we have labels. These labels are actually here, they are shown as colors. Labels are what? K, B, and I. Time of birth and index. Right? And this is what the filter returns. There are sometimes misdetections, there are sometimes, you see, false alarms returned by the filter. That's all right, because we have heavy noise and heavy false alarm. But practically, this should be okay if it happens like a dot here, not sustained. Okay, now we get to the main point, and I have another 10, 15 minutes. Am I right? Yeah, until 10 a.m. I'll finish at 10. 10 a.m. So, do you remember the card that was object number 0? See, it is connected to these, and they are connected to others. Each of them have a multi-object density, like L and B, a set of R's and P's. Probability of existence, particles and weights for each probability of existence. The pi 1 is coming from car number 1 round, pi 5, pi 2, pi 4, pi 3, right? And then this one receives a pi 0 from here, a pi 5 from here, pi 6, pi 8. And every one of these, we need to fuse these multi-object densities to get better results. Because each of, and then this fuses all of these, plus the one that it has formed local. This one fuses all of these, the 3, plus the one that it has formed locally, and so on. This is multi-object density fusion. Why do we do it like this? Because, as I said, your agents may have different types of sensors. There may be different ways of how they process their full sensor measurements. But first, we have translated all of them into multi-object densities like R's and P's, and then now they speak the same language. And regardless of what the car gets, what sensors they are, we can talk about information fusion this way. Information fusion that is statistical. So it not only fuses the information, but also the uncertainty and tries to reduce them. Tries to reduce the uncertainty. So I have a more standard, more confident response. So that's how we define at every time k, I have pi k's on to up to n tens. And this is the number of sensors around. And I want to fuse these pi's. I want to find the fuse density that is optimally combining these MODs. So what is our approach? We use an information measure called regular divergence. It actually minimizes the similarities. Let me show. So, see, I want my mesh, my fuse density to be such a way that its distance, its difference from every given density when I add them all these differences with weights according to sensor. This sensor is more important, that sensor is less important, so I give this sensor more weight, and my fuse density should be more similar to that sensor than that one. Right? But this is a similarity measure. Difference between densities, right? For that regular divergence. And I want to get the fuse density that is as similar as possible to all the ones that I have. So practically, I'm looking at overlaps. I'm looking at overlaps. My fuse density should declare something that is confirmed by all of these sensors. If all sensors are saying that, oh, there is a target here moving this way, if all of them are saying that, then my fuse density should say that as well. But if one sensor is saying that there is a target moving this way, and other sensors do not say that, then it shouldn't be confirmed by my fuse density. That is the way to avoid double counting and to manage information efficiently. It is mathematically proven that when I use pullback label divergence, it does that. It is efficient in terms of information loss. It maintains all the useful information, and it avoids double counting. This is the definition of pullback label divergence for 2. This integration is over sets. And if we do the mathematics, I skip the mathematics, they are important, but we don't have time. If your RKs and PKs are like this, see, for one label L, RK that is given from sensor 1 is RK1, and you have RK2, RK3, and so on, and PK1, PK2, PK3, and so on. Then, when you apply that formula, then minimize them. So this becomes the formula of density. And when you put this formula into the minimization, this gives you the merged probability, the fused probability of existence, which becomes given by this formula. See, for that same level L, the merged diffuse probability of existence is this. This is the geometric mean. The geometric mean of all the probability of existence given for that label by different sensors. Geometric mean with different weights. They are sensor weights. And this becomes the formula of merged density. And if you apply particle approximation for the densities, then this becomes the formula of fusion of R. This is omega, this is double. This is particle weight, this is sensor weight. And this becomes the formula of particle weights after. Here's an example. Let's say in that same scenario, you have 4 sensors, but their measurements are only bearing angle. For example, they are microphone arrays. They only measure sound, directional arrival of sound. And airplanes are flying through, they get the sound and give you 1 angle each. How do we fuse all these information? So if you want to use this is the result of fusion. Note that you can't get it with 1 sensor, right? Because you only have angle. But when you fuse the 4 sensors, this is what you get. There are still a lot of errors because the angle is very erroneous. We have taken the angle to be very erroneous, about 5 degrees. And note that 5 degrees, if your target is here, 5 degrees for this one is not a lot of error. But if your target is here, 5 degrees of this angle is a lot of error in location, right? That's why that's the best that you can do with your filter. For example, during this time, your ground truth cardinality is 4 filters. But for an extended period of time, you are missing 1 or 2 targets. Why? Because it is at the time of entry, and at the time of entry, 1 or 2 sensors are giving you very large errors in position. If you have limited field of view, due to this equation, if there is a target that is not detected with one sensor due to being out of field of view, then the diffusion equation is like this. One R is small, your fused R will be small. The problem that we have is this, that with our fusion method, the target appears, an object appears in fusion if it is detected and measured by all sensors. So if you have limited field of view, you have to be patient and very careful with how you use the formula. Fortunately, this is our own work that we discovered that the mathematical derivation of the fusion method doesn't need this sensor weight to be the same for all labels. Of course, you have, for example, NS sensors, these weights over the sensors should sum up to 1, but for one sensor label, you may have, for one object label, L, for that object, this sensor is more important, this sensor is less, and for another object, this sensor is important, and that sensor is less. So we mathematically proved that you could have this omega I, the sensor weight, dependent on the label. Here's an example. Let's say you have the same 4 bearing angle measurement, but with limited field of view. For example, this one, this is its limited field of view. This one, this is the limited field of view, and so on. But if you use the normal fusion method, only the objects that are here will appear. And it actually will fade. As you see, this is fade. But when you apply your formula with omega i's that are dependent on label, then it works. Provided that you define these labels properly. For example, what we did is that we say, if I have an object L and a sensor I say, what is the probability of existence of that object L determined by sensor I? And what is the probability of that object determined by all the other sensors? And I use this formula. If I use this formula, if there is an object in the field of view of this sensor, its R will be big, and this sensor will have more weight. But if it is out of this sensor, its R for that object will be small, and the weight will be small. This way, I incorporate the limited field of view. You see, think this lesson that you want to take home from this talk is this. This was a practice of interpreting what we have in mind and we talk in our own spoken language into mathematics, incorporating information into a mathematical algorithm. That is what you need to do to be able to write good papers, come up with good ideas. That is the skill that you. Otherwise, nowadays, everybody, even ChatGPT, can code. If your work is entirely coding, it may not have the scientific impact that you're looking for. The scientific impact in our stream of work is in this, right? Mathematical formulation and implementing of that into our solution. Anyway, so when you apply that with weights, with sensor weights, this is what you do. Let me skip these challenges because I have only 1 minute, but can you please share these slides with the audience? And I will jump into conclusion. So, as I said, in very short words, we have information acquired from sensors. The best thing that we do is we turn those informations into probabilistic forms, like this. And if the information involves multiple objects, we have multi-object density, right? And then agents connected in a network, they share information. What do they share? Density. And in each agent, these densities are fixed. In this talk, I presented how we can form these densities. One way of forming these densities to incorporate all the uncertainties, and then how we can fuse these densities to minimize uncertainty. That was the main thing that we covered. And yeah, if there are any questions, thank you very much. Thank you so much.
So we have the question because it's over there, and we get people. So in the meantime, let me explain the story with my student so we can understand well. And so in the meantime, please take a copy. We prepare a copy for you, and we have some requests, and yeah, giáo sư vừa mới trình bày tức là mọi người nghe đúng không? Thì là cái bài của chúng ta hay liên quan đến cái phần mà dịch bệnh đa nguồn và cái thông tin hỏi này là bây giờ là chúng ta có một cái cảm thấy đơn đấy. Vừa nghe thông tin là AI dần không? Thì bây giờ mình có rất nhiều cái dần những cái dần lung la người thì có người ra một cái quyết định xe đường có người xe một xe có hành vi đi riêng thì làm thế nào để tích hợp các cái trong một trạng thái mạng lưới không hẳn giáo sư lấy được qua một cái tức là cái và như một cái mai thì cái đấy chúng ta học rồi quay những cái bài thì đề nghị là chúng ta cũng nghe mà cho thêm một câu hỏi biết là những em nào muốn đi du học mình học một master và những linh thứ hai là có những cái chung và từ I should explain in Vietnamese the brief of your patient, especially the mustache. So it's very honored to mention them. And especially because right now, you know that in our year, we can focus really on information. You know that we have done a lot of Kenya, right? Here in Kenya, we have a new term, AI agents. Yeah. So how can we combine the space and everything from which AI agent? That should be how we mention our. Yeah, and hopefully that right now, because we have the new funding from VNU, in future, we will very famous company in Vietnam. They are led by Mr. Luc. They are the owner of the Future Brand. So they gave the new funding for every science and every research is looking in Vietnam. Our VNU. We think I have for 2025 this year. I just opened the report. And it lasts till May 31, but 31st. So I think that we can figure out why the new between around new and
I have an idea.
Yeah.
I have an idea. Yeah. Very briefly, the idea is like that. You have several agents. Each of them are generative AI. Right?
Yeah, sure.
What a generative AI agent does is to learn a very high-dimensional, complex distribution.
Yeah.
And its output is one sample of that distribution, right?
Yeah, sure.
Because the input, the output is one sample of that distribution. So combining multiple of these for better performance is combining or fusing distribution.
Yeah.
But we can work on that. We can actually formulate and come up with closed form or optimization oriented responses to that problem for combining these agents. which would save the training time until one of the papers arrive.
That's I totally agree with you because right now, you know the VNU, which me myself have just been a key member of the sport member who's writing proposal to military congratulations of investment and planning. But now it is in my way to material finance. So in last year we have to write a proposal to asking for money for granting for new server for building for what funding AI application. But we have to wait. But my question is that how do we do AI without the supercomputer like A100 or H100? Oh, this is fine. So we myself think about the new solutions. Like let's say AI agents like was created before, somehow in a small name or somehow in any support. So I think that's where we cannot wait for supply or a server from military of finance or so I think that is quite important. And if you think that is important, you can go ahead. For VNI information, can get search from internet for version you see. It has no reason to panic. At least can to 1 million. If we can prove that is the feasible and we have a lot of experts in not only Vietnam but also from international. Because the review of what also we have the last 3 rounds. The first round from the Vietnamese studies, and the second round from international studies. USA, European, and Australian. And last round, interview round. Now, she had only 10 or 5 to 10 projects passed to grant came to interview round according to the mother from the world. So he decided, okay, this is good. We have or you have a many potential for continuing connecting to solve the real world application, real problems. And for example, in the last year, I have just witnessed Brian from the future. We get Brian for solving some problem climate change, but with the support of AI and for automatic and so I think that we can solve the problem with other ways. Yeah, because we are
that's why I'm here.
Yeah.
On such opportunity.
Right. We are mathematicians, we are AI scientists. So we need the real problems. So that's the way we do it. And I think I will send you the computer report. So let's raise some ideas.
You have the best expert in AI and machine learning here. Yeah. And my area is mostly in statistical information fusion. Yeah. So I think we have to combine expertise for collaboration on such projects. Yeah. And we have a lot of feedback in Melbourne as well.
Yeah. I really need your support together. So actually, I emphasize in the first time, so only the AI studies, but also the other studies. So we can find together, and that's the way we solve the problems, and that's the way for scientists. We truly scientists, right? Okay, so I think that right now we have some questions from our here. Sure. And firstly, we have 10 professors on this discussion, and now for Q&A. So, Professor,
questions?
Yes. So, thinking about how is it implemented in real application?
In real application, what do you mean? You're talking about hardware or software?
In terms of hardware.
In terms of hardware, I could imagine. So one real application, one real implementation that my colleague has done was running this big filter on. So he wrote the code in Python. It was running on the Samsung mobile phone at the time, 5 years ago, not today's Samsung, right? And it could track up to 1 million targets. But he developed that for space debris. I could imagine that, for example, in the new autonomous cars, you don't have an ECU, you have a multi-GPU processing unit, and this would the model, the propagation of these particles and their weights. That's what we're talking about. Probability systems, particles and weights. The propagation of them would be probably 1% computation that is needed for a deep learning algorithm for millions of weights. You know, just without training, the algorithm running forward would be 100 times more than the propagation of these, because you need maximum 10,000 particles for about 20 objects. 10,000 particles per object. That would be, 400,000.
I take it from your answer that it's very feasible computationally.
Absolutely.
Therefore, it can be applied to
computationally. It is very feasible. Otherwise, we would go deep learning. Yeah. Otherwise, it maybe it enjoys practical solidity and computational.
So right now here we have many students working on deep reinforcement and reinforcement for some kind of these programs. So really good. So we come from VNPT, one company in Vietnam.
Thank you.
Thank you so much for this. A lot of mathematical combination. It's great. It's great to hear to deploy this for Python. And that's plenty of it. And my question is, we are doing BRB problem. BRB being called routing problem, and in nowadays we are seeking for some new methods. One of the methods is deep reinforcement learning. Maybe I take some familiar in the part, the previous step, in the first step. Maybe we have some familiar in deep reinforcement learning. And my question is, could we do a co-research, or could you explain more on how to deploy deep reinforcement learning in the problem?
Thank you very much. So, deep reinforcement learning and deep reinforcement learning are not related to statistical information fusion. But luckily, I have worked on that. Actually, in my ITI Technology Seminar, in addition to the keynote, I also presented 2 papers. One of them was about deep reinforcement learning for controlling a quadrupedal robot with 4 legs. For mathematical formulation of your problem, like any other problem, I'm not familiar with the specifics of your problem, but first, with reinforcement learning, you have a controller and you have a system model, right? Your system model has inputs, which are actions that are coming from the controller, and they have outputs, which are the state of the system. And your controller meets the definition of the rewards. Right? So you need to mathematically model your system dynamics, which is the relationship between output, the state, in terms of the actions that the reinforcement learning controller will generate, right? And your reward function, which is at the core of your controller. This is where you need mathematics. Then it becomes deep when, for your controller, you use a deep learning model. For example, Normally, for the controlled robot, where the actions were 16 dimensions, 16 joint commands to be sent to the motors of the legs of the four robots, right? There were four joints on each leg, 16 dimensions. For that, in the new paper that I devised, I had a hierarchical level, so a high-level controller and a low-level controller, because in reinforcement learning, what you have is optimizing the controller performance in a spread of time, in a sequence of time samples. So you define and minimize your reward as the sum of rewards in a number of consecutive times, right? So the single modeling becomes important in modeling that reward. It should meet the critical requirements of your technical problem, right? Otherwise, throwing a deep learning model like a fully connected network and training it is not much value. That is not in for research applications. Even I don't know the specifics of your problem, the number of inputs that model will have. If the inputs are images, then just a fully connected network will not work. You need to use, for example, ResNet version 9 for that. You need to have a very good model. So I hope that answer was done.
Thank you so much, because Mr. Lucas over there is here working for VNU&RMIT. So one of the problems in VNU&RMIT for transferring goods or items to many customers. And so given that they have a treat to proceed a map, so we would like to have the routing for sending the goods and item on the depots to customers. And in that way, it's very similar to the where we have so many customers. And we brought together as a
non-linear program.
Yeah, online. So if you came from the VIP, the people developers.
I'm more than happy to help as a consultant to look at company as a consultant. They contact me and check me.
Yeah. So if you have after this relation, this will contact you, and you will send some your best solution for the first learning to this. Okay.
So easy.
Yeah. In our ITI, we have many scientists and experts in IoT and AI combined together and smart control, and that usually will help you. So the head of IIT lab here. So W will have some questions.
Yes.
So thank you very much for very interesting presentation. So we are actually on another space is we more concerned about how to do computation efficiently so that we can, for example, you can this in hardware and can do it in real time. So when you talk about we can do it with multi-GPU, so I can imagine that this problem is a kind of very hard problem, especially when the number of states will increase and you I think in your presentation you said that you need to know about the label. So my question is so how hard is it in terms of the
Computation.
yeah, computation exactly, and memory also.
Thank you very much. That's a good idea. Thank you. Let me show. Oh. Answer your question, that you read the proper equation. Okay. So, in terms of computation, I said multi-GPU. I assume that you have an autonomous car And it is instead of an ECU, the normal cards have now an ECU, electronically controlled unit, it will have a large processing unit, multi-GPU, but not for doing that. It is multi-GPU for, processing images, deep learning, processing the LiDAR sensors or laser scans, meeting point clouds, classification, and so on and so forth. This part is easier. This part is not computationally demanding compared to deep learning, not computationally. Now, let me give you an example. You see, let's say you have maximum 100 objects to track. Maximum 100 objects. So you have 100 of these pairs in your model. 100 probabilities of existence and 100 state density, right? Let's assume that. Hold on. Here. Can you duplicate my what five things here in order to answer properly? If you can do that. Yes. It's going to fly. Yes. Sure. And now see the bottom. Okay, great. So I hope that people online can see the slides now because it was okay. Now let's say here on one. It's just over a new step, right? Just maximize. Okay, good. Yeah. Let's forget about typing. What's about to use typing? It's not visible. Okay. So let's say you have 100 objects. So if you're dealing with 100 numbers here, and then let's say your state includes X and Y and X dot and Y dot. For numbers, for the speed and the location. Orientation, that's 5 numbers. Also, your weight, the rate of orientation, that's 6 numbers. Also, class, which is the discrete number. 1 number out of 100 or 200 or 100%. So that is how many? 7 numbers, right? 7 numbers. And then, so for density, for example, for each object, you only need maximum 10,000 particles. 10,000 particles is a lot. Time for each particle, you need 1 vector, which is 7 numbers. So that is 70,000 numbers for particles, plus 10,000 weights, 80,000. That's 80,000 numbers for particles and weights, plus 100 probability of existence. Let's forget that. Totally 80,000. You are talking about propagating and calculating 80,000 numbers through prediction, step, prediction, step. And the algorithm is so fast. And for 100 objects, 100 objects. Deep learning does that on millions. For example, you see, you have an HD image. What is the number of pixels in an HD image? It is millions, or 2 million. million pixels multiplied by 16 if each pixel color is 16 bits. But if you're talking about 80,000, it's much faster. And most of the visual processing module, it can run in real time. My colleague is doing it on a mobile phone, running in real time. Was that a good answer?
So actually, it's because the data is actually depends on what type of sensor you are using. No,
That's the goodness about it.
but and also so for this method, so actually I think you have the assumption of there are some precondition. For example, it has to follow some kind of distribution, or it's a known source in terms of statistics. But in some case, for example, if it's an unknown source, for example, can it possible to estimate?
Thank you. Thank you. So first of all, it is not sensor specific. Remember, every agent has its own sensor. We assume that central processing has been done. For example, one of these cards is one of the, it only has cameras, multiple cameras around it, front, like Elon Musk cards. Lots of cameras, only cameras, front, images, they have been already, we assume that they have been already processed. Detections happening, detections have been fused. Fusion happening already through their algorithms, right? There's no algorithms, we don't care. What we have is of detections coming from what sensor, we don't care. This algorithm itself is regardless of the sensing. The actual sensing and pre-processing is a lot more computationally expensive than the statistical fusion algorithm. And it's also the beauty of mathematics, you know. Yes, of course, with deep learning, you may skip a lot of mathematical analysis, and the computer does the hard work, but it becomes computationally expensive, right? But if you do mathematical modeling properly, and as close to reality and as realistic as possible, we get rid of all that load, and it still gives you roughly the same answer. Wrong. In ICIS and conference, it was a good conference. Actually, acceptance rate was below 30%, which is really good for, you know, conferences. There were lots of papers on reinforcement learning. And what I realized, in one session, there were 5 papers. What I realized was that the accuracy by mathematical method, non-deep method, which was much faster, right? The accuracy was like 92%, and then looking deep, it became 95%. Practically, there is not much difference between 92 and 5%. So that's about different sensors. This platform is sensor independent. I hope I could answer your question.
Yeah, I totally agree with you that because right now we have trained for the extendable AI. So this means that we combine everything the record model into learning and with the supply of this display model. And especially the management model like with event, I think the which of those could combine in between the deep learning and display. And here, in our research lab here, we have many students. We're working on harmony between the deep learning and knowledge model. We have from Mike. This is now a lecturer in RMIT University in Vietnam, and also he is working final year in this. So, Mark, you have the question. You see that in this page. So your final is very different from the first year.
So I have a question. You have mentioned about the probability hypothesis density and also the generalized level Multi-Bernoulli and level Multi-Bernoulli filters. right? So my question is, how do the difference in the computational complexity is related to what Dr. asked? And what I'm adding is the tracking performances of the RX filters, such as the LNB and the LNB.
Thank you very much. Thank you. First, PhD filter, probability hypothesis density filter. That is another approximation of random finite set filters, like the LNB filter. But in there, instead of having probability of survivals and densities, you approximate the whole multi-object density and the Poisson density. With a Poisson density, the number of objects are Poisson, random variables, and given the number of objects, their densities are all IIDs, identically, independently, with the same density. And with PhD filter, what you predict is the parameter of its Poisson density for cardinality and the density for IID, one density. So it is much cheaper and faster than LNB. But it doesn't have labels. So what you can do is you can only estimate, you can't track it. If you want to create trajectories of your objects, you need to run data association separately. You need to relate, and every scan, you need to relate your objects with different objects in the previous scans. Give them labels. Right? PhD filter doesn't do that automatically. Normally, people use heuristic algorithms to do that, which work, but not as good as LNB. In the LNB and GLNB, generalized LNB filter, these stuff are mathematically implemented in the filter and consequently more accurate. So LNB is computationally more expensive, but still nothing compared to the LNB model. Still fast. It can run up to 100 targets. It can run in real time with current fast CPUs or even embedded program like Jetson. On Jetson, it can run in real time, 25 scans per second, 100 objects. With GLNB, it is even faster. GLNB, it is even faster. But and more accurate than PhD. But PhD filter is very simple, and it was the stress filter that was invented in RMS filter. That's why it is still very well known. But people are getting to know and use LNB now. For example, I have overheard that even Lockheed Martin is starting to use GLNB and LNB filter in their tracking programs. And in their latest tracking program, they are using PhD filter.
So you have any question? Okay. So thank you so much. And I think that because of time limitation, so if you have question.
Last question. Last question. I'm not so many questions. It means that actually they understood what I was talking about. If there were no questions, then it was a bad sign.
Good morning for President. Thank you for the presentation. And then what?
Good to know you.
Very good to know on several parts. I want to clarify some information. First of all, you were saying that since that we have both ways with the camera. First thing, the camera, when you see the object, it will call the object in the form of density. See another hand is from the power in mathematical. I want to understand your idea behind the presentation. So you're saying that when the camera recovers the object, for example, a car, so record auto vision. for example, the speed, the direction, the type, are. You are saying that this type of equation will be can be represented as a kind of distribution. So I question that for example, the camera one, the right of the object is a kind of density. So for the other camera, if the camera one of the check to the other camera, it will just say that some kind of fusion formula to combine all the density of all camera into one distribution, and it will give you a plot all the relation.
Yes,
So that's the idea.
that's the idea. If you want to do multi-camera fusion, that's the idea. Yes.
That's the idea.
But I can clarify what is involved. Finished with your question?
Yeah.
Okay. So, you see, let us say, thank you very much. Let us say that in this room, you want to do multi-camera fusion for people tracking. Easiest example. People tracking in this room with multiple cameras. I already see one camera there. Right? Let's say there is another camera there and one camera here. Right? You know the intrinsic parameters of the camera. Intrinsic parameters were fully calibrated. You have run the MATLAB code using the chessboard for calibrating the camera, right? Intrinsic parameters, or even the extrinsic parameters as well. But you can use deep learning algorithms for self-calibration of these cameras as well. Each camera takes an image, and then using the calibration parameters, it gives you, the camera gives you a blob in the 3D world, in the global coordinate system that is same for all the other cameras. That blob is a detection, right? But that detection has uncertainty. Now, you model that uncertainty. For example, your blob has a center X, center Y, width, height. 4 objects, right? 4 components. X and Y of the center, width, and height. Then you say, okay, I have a 4-dimensional Gaussian. The peak of this Gaussian is at the location of my detection. The peak is at the center, X, Y, width, height that I have detected. That's my density. And then there is a covariance. The covariance, for example, it could be dependent. Could be dependent if an object is close to the camera, then it has smaller covariance in X and Y, higher covariance in width and height, because the object is going to be larger, and therefore the size dimension variations may be larger as well, depending on your camera. Let's say there is a camera here. There is a laser rangefinder here. It gives you a 3D point cloud. Processing that 3D point cloud, you don't get log. What you get is a 3D template of the object, right? And that template itself has X and Y as well. And width and size. For example, let's say a cube template, a rectangular cubic template. It has X and Y as well. But because it is here, and it is a laser rangefinder, $25,000 laser rangefinder, very high precision, right? You have the density, but very small covariance. A density that is around the peak given by the detection here, a very small covariance. Then what you do is you just, and each camera or laser rangefinder is giving you a lot of such detections, each density, right? You apply them in the local LNB filter in each camera, and you get an LNB posterior. Local filter gives you a posterior. Then you fuse these posteriors. Each posterior has a probability of existence and density.
You fuse these probabilities of existence, these R's, and these densities. This is what I could say.
I think that's all right. Very interesting that we might will solve a group problem rather than depending on the learning model. That's something like that. Very interesting.
Thank you. Thank you.
So, one question, the side question, do RMIT has a scholarship for master degree or PhD?
RMIT has PhD scholarships for international students. Yes.
I have a chance.
It depends on, so if you're a master's student and if you have published at least one high impact paper, and if your GPA in average grades are high, you have a high chance. So 3 conditions to have a high chance. 1 is doing your master almost finished. 2, having the publication. 3, high grades.
How about the detail?
Sorry?
How about I want the detail?
That's it. More detail is that girls have more chance than boys. That's more detail.
Okay, thank you so much, Professor. You have a third question?
No, I was going to say that my room is in room 611. If you want, and one day come to talk to me, I'm happy to look at your.
Yeah.
You know, my office is in room 611 and 6th floor, room 11. And if you want to come, just knock on my door, and I'm happy to look at your transcripts and things and advise you how you can basically get in touch with whoever at RMIT that might be related to you. If not, and I can sort of assess your chances.
Okay, thank you so much, Professor Reza, and I think that is a good time for us, and many questions. And I think that there are still many questions more, because we have an online meeting. Online meeting is some questions I heard that they'd like to know more about it, and also provide. But the invitation, okay? And I once again, I thank you so much. And I wish that we will have more time here in Vietnam, especially I would like to seek for opportunities to get you here, back you here, from more time, some months, maybe for the professor, or somehow you can think about the sabbatical for 2 months or 3 months. I think the professor do also happy for that, and we like some here.
I think that's a good time to have alcohol soon.
But it's pretty that because this time we have a very short time for you to hear or to present together. And I don't have time to take you for some place in Hanoi. But maybe the next time, right?
It was my third time visiting Hanoi, and I have seen pretty much everywhere. Love it. Beautiful city.
Yeah. So once again, thank you so much. And before we close our session today, we'd like to have a photo session, group session. Firstly here, and next I would like to invite both professors and handhold attendees here to come visit the AIC Center and some lab here in ITI. And for lab, we'd like to have a representative of the Department of Science and Technology. We will take a tour for you. And for AIC, we will take a tour for in our is over there. It's a safe law. Okay. So mời tất cả mọi người lên trên đây chúng ta chụp ảnh chung với cả giáo sư đây là. So we might be try on attending here come for in front of floor. Second photo.
Thế các bạn nam thì ngồi ở bên dưới.
Nếu vậy
Slide đầu tiên những cái trên là mình lên chụp ảnh chung là mọi ý tính nữa thì là con là như sinh viên môn này nó rất là nó rất là
Môn hàng các bạn ngồi thế này, các bạn ngồi thế này hoặc ngồi tí hơn. Nhanh cái chuyển lên. Thế, ngồi lên xong.
Nào em ngồi lên, không ngồi lên.
Có cầm lịch hay là làm khó bằng không? Gì có thích bằng không? Các bạn bỏ mấy chai nước xuống.
Chỉnh nhá. Chỉnh người hình nhá.
Đổi kiểu.
Bắn phim nhé. Like that, yeah, like that. Speed up.
Okay. Chịu được nó. Đoạn đấy.
Càng này thấy dịch ảnh cái vấn đề.
Để kế của em làm nhé.
Các đấy cầm những cái này cho thầy nhá. Sắp xếp về phòng thì cho nó từng đi không thể tấp này.